Hello students, my name is Kapil Mane and we are starting B.Sc mathematics classes on our channel. Okay, so we already uploaded some videos on real analysis topic, real analysis topic. Okay, Riemann integration, Riemann integration. On this topic, we already discussed some points, that is interval, okay, function, bounded function. Okay, so in between upper bound as well as lower bound, subintervals, or you can say partition, as well as we already discussed, that is a refinement of partition, and supremum and infimum of interval, as well as supremum and infimum of over the function f over the function f on interval AB. Okay, this much we already discussed, and after that the upper sum and lower sum. So this much concepts we already discussed, and these are our basic concepts to know. Okay, so definitions, okay, how they concept here. So we already discussed this much topic, so we know about upper sum and lower sum. Okay, so upper sum we usually define in, that is u phi f. Okay, u phi f, that is upper sum over the function of f on particular partition. Okay, so it is denoted like this, that is capital 1 m1 delta 1, capital m2 delta 2, and so on, capital mn delta n. So this is the series. Okay, so we need to define this series in summation, like let's say r is equal to 1 to n. Okay, capital mr delta r. So this definition is our upper sum. Okay, so we already discussed as well as this lower Riemann sum also. Okay, lower Riemann sum is usually denoted by L phi f, that is lower Riemann, sorry, lower sum over the function f on particular p. Okay, it is denoted by small m delta 1, small m2 delta 2, and so on, small mn delta n. So here it is, the delta n is the length of the particular subinterval, and m small m1 is infimum, right? So here it is, this is the series, so we need to define like this also. Okay, that is summation r is equal to 1 to n, r is equal to 1 to n, small mr delta r. Okay, and this is our lower sum of function f over the partition p. Okay, so usually here it is our capital M is supremum of that particular capital MR is collection of all supremum over the f, and delta r is length of rth interval. Okay, so whenever it is, which one we get rth interval, that means subintervals length. Okay, and here it is, the small mr is denoted like collection of all infimum over the function f, and delta r as usual length of subinterval, length of rth interval, or you can say subinterval. Okay, so these two definitions we need to discuss in theorem number 1. Okay, so let's see, by using these statements we need to prove one theorem. Okay, let's see the theorem number 1. Statement is, let f be a bounded function on interval AB, and let small m and capital M be infimum and supremum of f over the interval AB. Okay, so f be a bounded function on AB, and let small m and capital M be the infimum and supremum of f over AB. Then for any partition P of AB, we have to define, or we have to prove that lower bound is less than equal to lower sum of partition P over the function f, as less than equal to upper sum over the partition P of given function f, and it is less than equal to upper bound of given interval or function, you can say that. Okay, so this we have to prove that. Okay, so I will read once again. Let f be our bounded function, and bounded means, you know that bounded means which have, any function have lower bound as well as upper bound. Okay, that type of function we can call bounded function. So here it is, we can say that, okay, interval 1 as to 2 is given, so this function will be some, here it is, so this function is bounded, limited, so limited in between 1 and 2, that type of function we can call bounded. So, and unbounded means there will be no bounded. Okay, there will be no bounded, it can say here it is 1 and here it is 2, and the function is rising from, like, without touching point 1. Okay, that type of function we can say, unbounded function. Okay, these function have lower bound but don't have here upper bound. Okay, so but here it is, we have lower bound also and we have upper bound also. Okay, so I hope you clear the bounded function concept by using these two graphs. Okay, now we need to show that the upper bound is less than equal to lower sum of the given partition. Next, the statement is, lower bound is less than equal to lower sum of this given partition over f, which is less than equal to upper sum of given partition f over the function f, and which is less than equal to upper bound. So we need to prove this theorem. Okay, so before that we need to consider one example. Let's consider, so you will realize how we going to prove this. Okay, so example 1, consider 0, 1 be one interval. So I will prove this example on interval, and here will be, we need to prove on given function. Yeah, okay, so 0, 1 is our given interval. So we need to consider one partition, like, let's say when a is equal to 0, comma 1 by 10, comma 2 by 10, comma 3 by 10, comma 4 by 10, comma 5 by 10. Okay, so this is our partition, and I will take directly as 1 is equal to b. Okay, so this is our partition, okay, which we have considered. So here it is, the upper bound of this function is, that is upper interval or upper bound of this given interval is 1, as well as lower bound of this interval is 0. Okay, so by this we know that lower bound is, that is, small m b minus a is less than or equal to capital M b minus a. That is, small m means our lower bound, which is 0, less than or equal to upper bound, which is 1. So we know that 0 is always less than 1. So this condition is satisfied. Now we need to check whether it is the lower sum of this given interval which is greater than or not. Okay, lower sum as well as upper sum. So let me consider one by one. Okay, first I will define the lower sum. Okay, that is LPF, and we know that how it is defined, that is summation r is equal to 1 to n small mr delta r. So here it is small mr means all the infimum from this given interval. Okay, so I will split this series like m1 delta 1 plus m2 delta 2 plus m3 delta 3 and so on plus mn delta n. Okay, so next we need to take a sub intervals for this partition. So sub intervals I will define like I, R, okay, or I. First sub interval is my 0 comma 1 by 10. Another sub interval is 1 by 10 comma 2 by 10. Another sub interval is 2 by 10 comma 3 by 10. Another sub interval is 3 by 10 comma 4 by 10. Okay, and the last 5, okay, 4 by 10 comma 5 by 10. The last is 5 by 10 comma 1. Okay, so these are our sub intervals of this given partition. So by using this we know that infimum and supremum from this, we know that infimum and supremum from this sub interval and so on. Okay, so here it is, infimum for this sub interval is 0. Okay, infimum and supremum is 1 by 10. Okay, so we, by using this concept, we need to substitute here values. Okay, that is capital M1 value is 0 into delta 1 value is, delta 1 is like this. Okay, so you need to calculate delta like initial term 9, final term minus initial term. Final term is 1 by 10 minus 0, that is 1 by 10. Okay, delta 1 is our length of that particular interval. Okay, delta 1 is length of that particular interval, which is 1 by 10, plus m2 is lower sum, that is infimum of this second sub interval is 1 by 10 into delta 2. Again we need to consider for this final term minus initial term, we will get 1 by 10 here. Okay, plus m3, that is 2 by 10, 1 by 10 and so on, all these intervals. Okay, so 2 by 10, again 3 by 10 into 1 by 10 plus 4 by 10 into 1 by 10 and also 5 by 10 into 1 by 10. Okay, so these are our lower sum values or lower bounds. Now we need to solve this. Okay, this entire term will be 0 plus again 2 by 1 by 10, 1 by 100 plus 2 into 1 and 10 into 10 is 100 plus 3 into 1 divided by 100, 4 by 100, 5 by 100. Okay, so again we need to take a sum now. Okay, 0 plus 1 by 100, 100, I will take 100 common, so 1 plus 2 plus 3 6, 6 plus 4 10, 10 plus 5 15, so 15 by 100 we will get here, that is LPF value. LPF value we get here. Lower sum of this particular partition is 15 by 100. Okay, so now same we need to consider here, we will consider it is okay, or otherwise I can write here. Okay, so UPF, upper sum of the given function over the partition P, which are defined is summation R is equal to 1 to N capital MR delta R, which is equal to capital M1 delta 1, capital M2 delta 2, plus capital M3 delta 3, and so on, capital Mn delta n. Okay, so capital Mn means, so here it is, this is our small m and this is our capital M, right? So from this all corresponding subintervals, right? So by this concept we need to substitute our capital M1, that is the supremum of that particular subintervals. Okay, we need to substitute here, and delta 1 we know that the length of that particular subinterval. Just substitute here. Okay, capital M1 is 1 by 10, delta 1 is 1 by 10, plus capital M2 is 2 by 10, delta 2 is 1 by 10, plus capital M3 is 3 by 10. Okay, and 1 by 10, right? So again, plus here it is the 4 by 10 into 1 by 10, plus again 5 by 10 into 1 by 10, and the last is plus 1 because supremum is 1 here into 1 by 10. Okay, so by this calculation we need to sum. Okay, take a sum of this. 1 into 1, 1 by 100, plus 2 by 100, plus 3 by 100, plus 4 by 100, plus 5 by 100, plus 1 by 10, right? So now this we need to calculate this. So take this much calculation aside, the base is common, so I will take 100. I will take 100. 1 plus 2 3, 3 plus 3 6, 6 plus 4 5, 5 plus 15. So 15 plus 1 by 10, this term you can write here. Okay, so for this we need to write again, take a LCM common, just multiply with this term, you can get LCM, that is 15 by 100, plus you can multiply this term with 10, that is 10 divided by 100. So you will get how much? You will get, that is 15 plus 10 is 25 divided by 100. So this is the value of UPF. So here it is, we get UPF value. So by using this we know that 0 is our m, small m, which is less than equal to LPF, that is 15 by 100, which is less than or equal to, that is 25 by 100. Okay, which is less than or equal to capital M, that is 1. Okay, so we know that this 15 by 100 is less than equal to 25 by 100. Okay, and 0 is always less than equal to, so that much we need to prove in this theorem. So I hope you clear this concept by using this particular example. Okay, now we need to consider one by one. So here it is, we consider partitions first. So in this theorem also we need to consider partition first. Okay, like a1 a2 or x0 x1 x2 x3 up to xn is our partition. So like this we need to prove here also. Okay, after this example, hope you clear this concept. Now we will prove our theorem. Okay, uh, so bar this, let consider partition P is equal to partition P over interval a comma b. That is P is equal to, let's say a is equal to x naught, x1, x2, x3, and so on xr. Okay, so you can say and so on xn equal to b. This is our required partition for this. Okay, so we know that since f is bounded function over interval closed interval ab, then for any partition p, then for any partition p on ab on ab, there will be sub intervals. Okay, there will be sub intervals like this. So we can define I is equal to xr. Okay, so we can define xr minus 1 xr, okay, which have sub intervals. Okay, so I will define here over ab, there will be sub interval xr minus 1 comma xr. Okay, these are our sub intervals. Then for any then for then for then for every value of r we have, then for every value of, we can say r is a real number, so we can take any. Okay, r we have lower bound as well as upper bound. So any sub interval we have lower bound as well as upper bound. So here also in this partition we have our lower bound as well as upper bound. Okay, so like this interval also have lower bound as well as upper bound. Okay, so for this reason we need to write, that is capital small m is which is less than small m which is lower bound over the interval ab, which is less than or equal to small m r, that which are lower sum of this interval, which are less than equal to capital mr, and which is less than equal to capital m. These are supremum of our given bounded. Okay, so these things on only interval. Okay, so again we need to write like this same, this concept will be right. Okay, with delta. Okay, so whenever we will add with respect to lower sums with delta, we will get m into delta, which is less than equal to m r into delta r, which is less than equal to capital M r into delta r, which are less than equal to capital M into delta. Okay, so these are our lower bound, upper bound, lower sum, upper sum. Okay, so you know that these things we already defined like what? Summation of summation of n is equal to 1 to n, that is capital Mn, sorry, small mn delta n, which is less than equal to summation of, you can say, r is equal to 1 to n also. Okay, small mr into delta r, which is less than equal to capital Mr o. Summation of r is equal to 1 to n capital Mr into delta r, which is less than or equal to summation of n is equal to 1 to n capital M into delta n. Okay, and we know that how it's defines. We usually define these things in like this. Okay, so this is our lower bound, that is m of b minus a, which is less than equal to, this thing is our nothing but lower sum, that is LPF, and this thing is our nothing but, here it is, upper sum UPF, and which is less than equal to, this thing is our upper bound. Okay, so hence we got our required proof, hence the proof. Okay, I hope you clear this theorem by visualizing this example. Okay, and thank you. Subscribe my channel if you got interesting information from my side. Okay, like, share and subscribe.